Hey everybody, this is the last lecture for Chem 104 where we're introducing new material. You can shout and clap your hands and stomp your feet. I know it's been a long journey. So we've got one section from chapter 9 and we have a section from chapter 11, and that's going to be it. We're not going to do chapter 10. These two sections are long enough and I don't want to overwhelm you. So without further ado, here we go. The first thing we're going to talk about is properties of solutions. So we've talked a lot about electrolytes. We've talked about solutions in terms of concentrations and the different ways you can calculate concentrations. We've talked about diluting solutions, dissociation of water and weak acids. Now we're going to talk about properties of solutions. So solutions are transparent. They don't separate, and they have small particles or ions that you can't filter out. So one good example of this would be salt water. You can't see the salt in there, you can't separate it out, and you can't just pass it through a membrane and get the salt out. A colloid has medium-sized particles. You can't filter it, but you can separate what's suspended in your colloid with a semi-permeable membrane. If you've ever done the experiment when you were a kid where you mixed cornstarch and water, that is a colloid. So you'll catch it if you use a semi-permeable membrane, but you can't really filter it. It feels kind of squishy in your hands. You can compress the cornstarch, but if you mix it around enough and get all the cornstarch up off the bottom of whatever container you're playing with it in, it just looks like cloudy water. So that's a colloid. Here are some other examples of colloids. So dust, smoke, fog, hairspray, all kinds of things, your blood plasma, paint, gelatin, lots of examples of colloids in real life. The final category is suspensions. So you have suspensions that are heterogeneous, they're non-uniform mixtures. So there's big particles that settle out of solution, and you can absolutely filter it. You have to stir them up to keep whatever it is suspended in your solution. Blood platelets, those separate out if you let it sit long enough. Muddy water, if you were a kid and you go play outside in the mud, you know what that's like. If you've ever had chicken pox or had a run-in with poison ivy or poison oak, calamine lotion was your friend. That is also a suspension, and it's quite soothing. So again, these are some real-life examples that you can use to help you remember the different properties of suspensions, and we talked about colloids and solutions. This is a comparison table of solutions, colloids, and suspensions. This is a very handy table. It will help you when you're doing your homework, and it'll help you to study so that you can figure out the difference between these so that you can identify different mixtures. This is another slide that talks about the differences in another way. So suspensions settle out of solution. So you can see these red squares, they're settling to the bottom. That was suspended in solution. B, you can see that the suspension, so the red, again, that's getting caught in the filter. So suspensions can be filtered out, whereas colloids and solutions cannot be. Then there's a semi-permeable membrane. You can see that these orange circles are still getting outside of the semi-permeable membrane. That's from the solution. So think about salt water or something like that. You're still going to have sodium ions and chlorine ions kind of going back and forth through the membrane because they're not stopped. They can go through the membrane as they please. But the colloids in the suspension, so the red squares and the green triangles, those will be stopped by the membrane. So this is just another visualization and another way to kind of quiz yourself what will be stopped by a filter, what would be stopped by a semi-permeable membrane, that sort of thing. Let's go through a learning check. A mixture that has solute particles that do not settle out but are too large to pass through a semi-permeable membrane. What would that be called? So they don't settle, but they can't pass through a semi-permeable membrane. Well, a solution, we said that's like salt water. So that can't be it, because it would pass through the membrane. Suspension settles out of solution. And this says that this mixture does not settle out of solution. So it can't be C. That leaves B, a colloid. And if we think about what a colloid is, it is too large to pass through a semi-permeable membrane, but it will not settle out of solution. To be able to do that kind of reasoning with your understanding of solutions, colloids, and suspensions. Since we're talking about things being dissolved in water, those different solutes affect freezing point and boiling point of the solvent. It also affects the vapor pressure. So the vapor pressure above the solution is going to decrease when you add solute. So our example is going to be you're boiling water to make some pasta, okay? You usually salt the water, otherwise your pasta is going to be bland and nasty. If you want your water to boil faster, you're not going to add the salt right away. You're going to wait till the water is boiling. Then you add some salt, and you might see the boiling kind of slow down a little bit, and then within a few minutes, the water's back to boiling again. You added a solute to water, and that changed the vapor pressure and the boiling point. So when you add solute, you're going to increase the boiling point. So our shorthand for that is an up arrow BP. That's our boiling point. The vapor pressure above the solution is going to decrease. So that's VP, vapor pressure. And the freezing point of the solution, so if we were to freeze the salt water, it's going to decrease. So SP is our freezing point. These different properties depend on the concentration of solute particles in solution. Let's talk about them a little bit more individually. When you're increasing the concentration of a solute in a solution, what you're doing is making it so that there are fewer solvent particles at the surface, simply because you've introduced another particle. So now that particle is competing. So let's say again that we have our salt water. If you just have water, well, there's going to be water at the surface. It's going to be fine. You add the salt, now some of the sodium and the chlorine, that's going to be competing for this top spot, okay? The top layer, the top surface of the solution. That's going to prevent some of the water molecules or the solvent particles from leaving the solution. And those particles leaving solution is what vapor pressure is. So when you add solute, you're going to decrease the number of solvent particles. With boiling point, what that means is with the vapor pressure, it's connected to the boiling point. If you have to have more heat to get more of your solvent to the surface, then that means you have to raise your boiling point. More solute particles are going to make your vapor pressure lower. We just covered that. So more solute means lower vapor pressure. That means if you lower your vapor pressure, you have to decrease your boiling point to compensate. It is going to take more energy for that solvent to get to the surface and to be liberated. The freezing point, we have to think about it a little bit differently. If you've lived in any kind of a cold weather climate, I was in Michigan for several years, I was in Pennsylvania, New Jersey, I've been all over the place. And before a big snowstorm, if you have a city that, works well, you're probably going to see salt trucks on the road. And they're going to be salting all the major roads to prepare for the snow and the ice. What that salt does is it makes it so that the snow and ice, if you want to prevent ice formation, you're going to actually start melting that snow. It's going to depress the freezing point of the snow. The reason is because you're increasing the amount of solute, so you're adding salt, and that's going to decrease your freezing point. So those solute particles prevent that water in the snow from creating its little lattice that's formed when you're making ice. The particles that are in solution, what we're really talking about is electrolytes and non-electrolytes, which we covered a bit earlier. Non-electrolytes dissolve as molecules. So our example for that is like table sugar. But a strong electrolyte dissolves entirely as ions. And again, our example for that is table salt. Here's another example of a molecule that dissolves in water, antifreeze. You need that in your car. And when you dissolve that in water, you're not breaking up this molecule. You're just surrounding each molecule with water, which is what that AQ is. It's aqueous. However, if you take sodium chloride or table salt, that's a strong electrolyte. It's going to completely dissolve in water. So you're going to make 1 mole of sodium atoms and 1 mole of chlorine atoms for every mole of sodium chloride that you dissolve. So effectively, you have 2 moles of particles in solution for every 1 mole of NaCl. So this is an equality. Remember those equalities from chapter 2. So a conversion factor, which looks like a fraction, could be 2 moles of particles for every 1 mole of NaCl. And you'll see why it's important that we can write this conversion factor in just a minute. So if we look at the effect of solute particles on boiling and freezing points of water, we look at pure water, the freezing point is 0 degrees Celsius, the boiling point is 100 degrees Celsius. If you add 1 mole of antifreeze, which is a non-electrolyte, then you're going to have 1 mole of particles that you add to this water. And that is going to depress or lower your freezing point of water by 1.86 degrees Celsius. If you add 1 mole of sodium chloride, we said that's a strong electrolyte. So you're actually going to have 2 moles of particles in that 1 kilogram of water. So instead, you're going to get 3.72, minus 3.72 as your new freezing point, which is 1.86 times 2. And if you have 1 mole of calcium chloride, that's 3 moles, because you have 1 mole of calcium plus 2 moles of chlorine. Remember that subscript on the chlorine means there's two atoms in each of these molecules. So that equals 3 moles of particles for every 1 mole of calcium chloride. And you have negative 5.58 as your new freezing point. And that's 1.86 times 3. Now remember, the freezing point, we're going to take the temperature of the solvent, which is water in this case, and subtract our change in temperature. The boiling point, however, we're going to take the temperature of the solvent and add our delta T. And here you can see that it's different. 1 mole of particles gives you a change of 0.51. So remember this change. For water, it's 1.86 degrees Celsius for every 1 mole of particles, and that has to do with your freezing point. For the boiling point, it's 0.51 degrees Celsius for 1 mole of particles. And that's your boiling point. And we'll put these to use. During freezing temperatures, calcium chloride is spread on icy highways to melt the ice. Calculate the freezing point of a solution containing 0.50 moles of calcium chloride in 1 kilogram of water. So the first thing that we're going to have to do is figure out how many particles are in 0.5 moles of calcium chloride. Then we're going to use our conversion factor to calculate our change in temperature, which we're going to call delta T. Finally, we're going to subtract our delta T from the freezing point of water. So for calcium chloride, we already said on the previous slide that calcium chloride has 1 mole of calcium ions plus 2 moles of chlorine ions for a total of 3 moles of particles. We only have half a mole of calcium chloride, so we need to figure out how many particles that means. We use this conversion factor (3 moles particles for every 1 mole of calcium chloride. That gives you 1.5 moles of particles, because our moles of calcium chloride cancel out. We take that 1.50 moles of particles, and we use our temperature conversion factor from the previous slide, which is 1.86 degrees Celsius for every 1 mole of particles. For this, you're going to end up multiplying the 1.5 moles times the 1.86, and that's going to give you 2.79 degrees Celsius, because again, our moles cancel. The third part, because we're not done yet, we know we have a change in temperature, but we don't actually have the freezing point yet. So our freezing point is going to be equal to 0 degrees Celsius minus 2.79 degrees Celsius. So that's 2 minus 2.8 with 6 figs. So it'll go through this very quickly one more time. The first thing we have to do is figure out how many particles we have in 0.5 moles of calcium chloride. We first had to figure out how many particles we get per mole of calcium chloride, which was 3. And then we multiplied our conversion factor of 3 moles of particles for every 1 mole of calcium chloride by the number of moles of calcium chloride we were starting with, which was 0.5. Then we took the moles of particles and multiplied by our temperature conversion factor to figure out what our change in temperature is going to be for our freezing point. To calculate the freezing point, we take the initial freezing point of water, which is 0 degrees Celsius, and subtracted our temperature change, and that gave us a negative 2.8 degrees Celsius. Remember that if you're doing a boiling point, you're going to add your degrees Celsius, so whatever change you get, you add. Now we're going to talk about osmosis. So we've talked about the properties of solutions. We've talked about freezing point, boiling points, and vapor pressure. Now we're going to talk about water flowing from lower concentrations to higher concentrations and vice versa. Osmosis is when water or your solvent flows from a low to a high concentration. So if you look at this image on the right, there's some kind of solute in here. Okay, there's sucrose, which is sugar. On the left of the beaker, there's just pure water, and there's a semi-permeable membrane that is separating these two solutions. The water can flow through, but the sucrose cannot, and that's because of something called osmotic pressure, which we're going to talk about in just a second. The level of solution on the solute side is going to continue to rise until the concentrations of the two solutions become equal. So there's enough water on the solute side that it's equal to the concentration of the water on the solvent side. Osmotic pressure prevents additional water from flowing once you reach that equilibrium point. The more solute you have on this side, so say you were to add a bunch more sugar, then that means that you're going to need higher osmotic pressure. So you're going to need more water, and you're going to have a higher osmotic pressure as you increase the amount of solute on your solute side of your semi-permeable membrane. So over time, you'll see the water level has decreased on the solvent side where it's just water, and the level has increased on the side that has sugar added. There's a process called reverse osmosis, which is used to purify water. You can actually buy reverse osmosis kits to purify water in your home, but it's also used in desalination plants. You can take seawater, especially a coastal state like North Carolina. If you are in the Wilmington area or anywhere along the coast, oftentimes they're going to use desalination to remove the salt from the ocean and use that water for tap water. So you have to apply a pressure that's greater than the osmotic pressure to overcome the natural order of things where the water moves from the lower concentration to the higher to in terms of solute to balance things out. This time you're taking the water from the lower concentration to higher. So if you had your beaker with your membrane, pure water, and then water plus solute, and draw some solute in there, you're actually going to get water flowing the opposite way in reverse osmosis. So that over time, what you would have is a higher water level on the water side than the water plus solute. That's why it's called reverse osmosis. So remember the difference between the two. If you can remember one, then you can remember the other is the reverse. So osmosis and reverse osmosis, those concepts are not limited to just, cleaning water and water treatment plants and things like that. We actually have isotonic solution running through our body, like blood, tissue fluids, and things of that nature. All of those things have solutes in them, and they serve a purpose, which we're going to talk more about that a little bit later in this lecture, actually, when we talk about buffers. When you're in the hospital, God forbid, if you have to have an IV placed and they're running fluids either to hydrate you or, whatever other reason, those solutions are going to be isotonic solutions, which means that they're going to have the same kind of makeup in terms of the amount of ions and things like that as your blood does, your other body fluids. You don't want to do anything to upset the balance of your body because cell membranes are semi-permeable. So you can have exchange of water across those membranes. You don't want to swell your cells. So those isotonic solutions usually include some kind of glucose or salt. If you have red blood cells in an isotonic solution, they're going to be fine. There will be some exchange, of course, but overall, the red blood cell is going to remain normal. It's not going to increase its size. It's not going to shrink. So those are normal cells. But if we put a red blood cell into a hypotonic solution, what that means is the water is pure on the outside, and is going to swell the red blood cell. Because there's a lot of stuff on the inside of the red blood cell. Okay? So it's going to keep sucking up water, because remember with osmosis, that water is going to keep going from the place of low or no solute to a place of high solute, like the red blood cell, until the concentration is equal. Well, unfortunately, that means that you're going to burst the cell, and that's called hemolysis. We don't want to do that because that's going to be killing off your red blood cells. If you put a red blood cell into a hypertonic solution, that means that you've got high solute on the outside, which outside is this water here, okay? And the red blood cell is a source of water, which means that you're going to have more water flowing out of your red blood cell than coming in. You're going to cause that red blood cell to shrink, and that's called crenation. That's also bad because you're going to deform your cells and you're going to be dehydrated. So we also have some individual slides to talk about this, so that if you didn't get it, you're going to get it because we're going to talk about it again. Hypotonic solution, we have more water flowing into the red blood cell. And it swells and bursts. And that's hemolysis. Hypertonic, you're going to have more water coming out of the red blood cell. Causes it to shrink, and that's called crenation. Also very bad. Now, you may have heard of dialysis if you have an older family member. Sometimes organs fail, like kidneys, and they have to undergo what's called dialysis. That is when you pass bodily fluids through an artificial membrane, and the large particles are retained. And waste particles like urea and things like that are removed. So it does the job of a kidney. So you're going to remove waste products, excess water, and things of that nature with the dialysis process. It takes several hours, and it's not fun. It's not fun. So hopefully you don't know what dialysis is from experience or from someone in your family. But if you do, you know this process is very essential for maintaining someone's life, because you need to get rid of those waste particles. So let's do a quick learning check to remember what isotonic, hypotonic, and hypertonic are. And I put this little bit of information down here to help you remember, because if I didn't have that, I would probably forget what the different concentrations of glucose and sodium chloride are too. So in an isotonic solution, we've got 5% mass by volume glucose or 0.9% mass by volume sodium chloride. So if you have a 2% solution of sodium chloride, that is above the 0.90%. So that's going to be hypertonic. Okay, that's more than the concentration of the IV solution. Glucose at 1%, well, that's less than 5%, which is in an IV solution. So that's going to be hypotonic. 0.5% of NaCl is again below the 0.9%. So it will also be hypotonic. And finally, 5% glucose solution, well, that's the same as what would be in an IV solution. So that's going to be isotonic. ISO is the same. So make sure that you understand the difference between isotonic, hypotonic, and hypertonic. Put isotonic in the middle. Hyper, you have a higher concentration. Hypo, you have a lower concentration. That should help you remember. Now let's do a learning check where we look at whether or not a red blood cell will experience a change or not. So it's no change. They'll undergo hemolysis, which you'll remember that is swelling and bursting. Or if they undergo crenation, which is shrinking. At a 5% glucose solution, that's what you would see in an IV solution, so that's not going to be any change. A 1% solution, well, that we said was going to be hypotonic, and that is related to swelling and bursting. .5% solution is also hypotonic, so we're going to swell and burst. And a 2% solution, that's much more. So that's going to be a much higher concentration on the outside. You're going to have the water flowing from the red blood cell to the outside, and you're going to shrink. Again, your understanding of isotonic, hypotonic, and hypertonic will help you understand hemolysis and crenation. So you cannot separate those two concepts. This is a concept map for Chapter 9 because we just finished it. And it will help you kind of put in perspective what we talked about in terms of solutes and solvents, electrolytes, and concentrations, all that kind of stuff. So it will help kind of give you a way to study and know how these things are related. Now we have to finish up Chapter 11. We're going to talk about buffers, which is absolutely related to what we were just talking about with the blood. So a buffer solution maintains pH by neutralizing small amounts of acid or base that are added to it. When you just add acid or base to water, you're going to see big changes in the pH. So if you have water, neutral water at 7, pH 7, if you add a little bit of an acid, then you're going to plummet your pH. It's going to go down, okay? If you add a little bit of base, your pH is going to shoot up, okay? If you have a buffer, you're not going to see much of a change. So if your buffer is at pH 7, you add a little bit of acid, maybe it'll dip down to 6.9. If you add a little bit of base, maybe it'll go up to 7.1. But you're not going to see any drastic differences. 6.9, 7.1, it's all about the same. Buffers work because they resist changes in pH. In your body, they're going to absorb the extra hydrogen ions or the hydroxides from the different foods and different processes that go on in your body. And you really need that because it maintains the proper functioning of your cells and your blood. So the pH of your blood is about 7.4. And there's a buffering system in your blood to keep that pH, because if it strays too far outside of that, you're going to experience cellular death and you're going to feel some real bad consequences in your body. So a buffer solution contains a combination of things. It contains an acid-base conjugate pair, which is a weak acid and a salt. So in this case, our weak acid is acetic acid. It does not fully dissociate in water. Most of it stays just the whole acid. And then for the conjugate base, what you can do is you can have sodium acetate or something like that that will dissociate and form that conjugate base. And it has equal concentration. So maybe you have 1 molar of each, equal concentrations, whatever it is. So like I said, for the salt, if you're going to have an acetic acid and sodium acetate buffer system, you're going to dissolve that salt and you're going to make your conjugate base. You're going to have a large amount of that, and it can absorb additions of H+. You're also going to have a large amount of acid, and that can take on a lot of the OH-. So you have to have large amounts of both your weak acid and your conjugate base, so that when you add little bits of acid or base, you're not going to see a big change in your pH. The equilibrium is going to shift when you add base or acid to a buffer system. If you add in base, then you're going to decrease your weak acid available, and you're going to increase your conjugate base. If instead you add a little bit of acid, then you're going to decrease your conjugate base because it's going to absorb some of that hydrogen and make more of your weak acid. So it's an equilibrium. It shifts back and forth depending on what's added to the system. So buffers have to work both ways. They have to be able to absorb additional acid and additional base. And they do this by having a weak acid and a conjugate base, which is made from a salt of the weak acid. The pH of the solution is maintained as long as you don't add a super huge amount of your acid or base relative to the amount of your weak acid and conjugate base that you have in solution. We can calculate the pH of a buffer. So if you remember, we took acids and we wrote these dissociation expressions. We talked a little bit about the Ka. So refresh yourself on that if this looks kind of foreign to you. But this is the expression for an acid dissociation. You have your weak acid concentration on the bottom, and then you have your hydronium or your H+ concentration. I write H+ because it's shorter than H3O+, so writing hydronium. And then you have your conjugate base. If we solve the expression for the hydronium concentration, we're one step closer to calculating the pH. To do that, you're first going to multiply both sides by your weak acid concentration. And since we're trying to isolate the hydronium, we're then going to divide by our conjugate base. And that's how we solve for the hydronium concentration. So the generic formula for this, so you don't have to go through and solve every time, is the Ka of your acid, which it changes depending on what the acid is. You're going to multiply that by a fraction where you have the concentration of your weak acid on the top and your conjugate base concentration on the bottom. And again, that's equal to your hydrogen concentration. Remember that pH is equal to the negative log of your hydronium concentration. So if you can solve for hydronium using the acid dissociation expression, then you can solve for your pH. So let's do a practice. The Ka for acetic acid is 1.8 times 10 to the minus 5. What is the pH of a buffer prepared with 1 molar acetic acid and 1 molar conjugate base? They give us the equation here so that we see, okay, this is the weak acid, this is the conjugate base, and we can write our Ka, our dissociation expression. Again, this is something that we did earlier on. So if this is foreign to you, you will need to go back and refresh how to write an acid dissociation expression. So you should be able to write that based on the equation that's given. Remember that water, we don't care about it because it's a liquid at constant concentration. It doesn't change. But everything else we do care about. And then from our previous slide, we rearranged this so that we knew how to solve for the hydronium. So I'm just going to rewrite that here. There's no 2 there. Getting a little too excited. Now we were told what the Ka is. It's 1.8 times 10 to the minus 5. And we're told the concentration of our weak acid and conjugate base. When you fill in those numbers, you'll see that the concentration of the hydronium ion is 1.85 molar. Okay? We're not done yet. The question is asking for the pH of the buffer. So make sure that you don't just stop here. That's not what the question is asking. The pH is related to the concentration of hydronium, but it's not the same. So the pH is equal to the negative log of our hydronium concentration, which in this case is 1.8 times 10 to the minus 5 molar. When you put that into your calculator, which don't forget, you may, if you have a TI-89, you may have to go to the catalog for the log button, but it's log base 10. And you want the negative of that. For sig figs, you're going to put down the first, what comes before the decimal place, which is a 4. And then you're going to write 2 decimal places because we have 2 sig figs in our concentration. So our pH is 4.74 with proper sig figs. Remember, pH sig figs are a little bit funky. So that's how you go from a dissociation expression all the way to figuring out the pH of a buffer. Because the Ka is constant at a given temperature, you can determine the amount of hydronium based on the ratio of your weak acid and your conjugate base, which is what we just showed mathematically. When you add a little bit of base or acid, it only changes that ratio a little bit. If you add a lot of acid or base, that may exceed what's called the buffering capacity of the system. So it can't handle that large concentration of acid or base added. You can use all kinds of conjugate acid-base pairs to make buffers. Phosphate buffers are very common, which are these two here. You'll also see bicarbonate and carbonate acid-base pairs, and that's kind of similar to what you see with blood. The pH of the buffer solution is dependent on which acid-base pair you choose. So you choose the one that's closest to the pH you're trying to maintain. If you want to look at how different ratios of the weak acid and the conjugate base, how those affect the buffering capacity, we can do that. And we're going to use an example with the phosphate buffer. Okay, so the Ka for that is 6.2 times 10 to the minus 8. When you write the Ka, the acid dissociation expression, and rearrange to solve for the hydronium concentration, this is what you get. I'm not going to go through and redo it, but just for your own practice, you can write the dissociation. So the whole Ka is equal to, and then the stuff on the top, stuff on the bottom, and then rearrange to get this equation for the hydronium concentration. If you look at different ratios of weak acid and conjugate base, you can see that there are changes to your pH. So to go from a lot of acid to and not a whole lot of conjugate base to not a whole lot of acid and a lot of conjugate base, you're going from 6.2 to 8.2, which remember, that's 20-fold, right? So each change in pH is a factor of 10. So that's big changes just by changing the ratio of your weak acid and conjugate base. So you have a lot of flexibility to make whatever buffer concentration you want, or pH you want. So let's link all of this that we're talking about with the buffers and different solutions to something in the body. So your blood plasma has a normal pH somewhere in the ballpark of 7.4. If your acid concentration in your blood causes the pH to fall below 6.8, or if you don't have enough acid in your blood and you have your pH rising above 8, you're going to have some major issues with cellular function. In your body, you actually continually make carbon dioxide. It's one of the products of cellular metabolism. And that is carried to your lungs. That's what you breathe out. You breathe in air, we take on the oxygen and some of the other gases, and then we breathe out, and we're breathing out carbon dioxide and other stuff that our body didn't take up. We're also breathing out the carbon dioxide that's made by cellular metabolism. Some of that carbon dioxide is actually dissolved in your body fluids. And you're going to make carbonic acid, H2CO3. It's a weak acid. And what does that mean? It doesn't dissociate completely. And remember that weak acids are also weak electrolytes. Whatever bit of acid does dissolve, you're going to make bicarbonate and you're going to make some hydronium. Your kidneys are also going to make more bicarb. And all of this sets up a buffer system in your body fluids. So you have the air that you're breathing and all of the carbon dioxide that you're making from cellular processes combining with water to make your weak acid, carbonic acid. That acid, yeah, we're going to have a little bit of dissociation, but your kidneys are going to supply this. So remember, we have to have a weak acid plus the salt of a weak acid in order to have a buffering system. And in this case, the kidneys are supplying our conjugate base, and that's what we need to make a buffering system. The excess hydronium is going to interact with the bicarbonate, and you're going to form more of your carbonic acid. If you have excess base in your body, then that is going to react with the acid, and you're going to form more of your bicarbonate ion. So this equilibrium is what keeps your blood at the proper pH. You can do all the things that we talked about in terms of the Ka and figuring out hydrogen concentration and figuring out the pH of your blood, what ratio, all of that math that we did, you can do. All you need is the the Ka. pKa is a whole different ballgame as a biochemist, that's what we care about. But you need the Ka of carbonic acid, and we already know, we have an approximation of what the pH is. So you can actually work backwards and figure out your concentration, or you can go forwards, and if you have all of your concentrations of the weak acid and the conjugate base, then you can calculate your hydronium and you can calculate your pH of blood. So that's a practice that you can do if you want more practice with the math from this section. So if your CO2 levels rise, meaning you're not, inhaling and exhaling enough, you're not getting enough CO2 out of your body, then you're going to increase the amount of carbonic acid in your blood, and that's going to lower your pH. That condition is called acidosis. If you have CO2 levels that are very, very low, then you're not making very much of the carbonic acid, and that means the conjugate base and the OH is going to be elevated. So your pH is actually going to be increased. And that's called alkalosis. So a high pH, that's something that's alkaline, okay? This table summarizes the symptoms and causes and treatments for both cases, when you have increased CO2 in your blood and when you have decreased CO2. It's a really bad thing, quite honestly. So high CO2 levels, say you're in the house like we are now, stay-at-home orders. If you're not airing out your house, your house has some natural ventilation, but increased CO2 levels, even if it's not necessarily, a lethal level, you can actually still experience some cognitive impairment. It can ruin your sleep and all kinds of things. So getting fresh air is really important. Likewise, you don't want to be hyperventilating, because you need some of that carbon dioxide. So either way you go on the on the extremes, you don't want to be there. Okay, that's all I have for you. A lot less math in these two sections, much more concept based. So I will be posting the practice exam for exam 4, and we'll go over it in class on Tuesday. If you have any questions about that before Tuesday, you can always send me an email. Until then, good luck.